Okay, this is a description of Dijkstra's algorithm for finding shortest paths. Now, there are two things we can do with Dijkstra. One is to have a starting point, so a source node, and a target one. Let's say G was my target. The other is to simply have a source node, okay? And then what happens is that you keep going until you have found the shortest path from this source node to every one of the other nodes in this graph. So this is called Dijkstra's. I will write his name. He was a famous computer scientist. I think I'm writing in white on white background, not very wise. Okay. So Dijkstra's algorithm. Please excuse my handwriting, especially with on this tablet. Anyway, so what I'm going to start is initialize everything, and the way you do that is first for the source node. Okay, please excuse this. The source node is at the beginning you say, so basically one thing I haven't yet said is that each node will have two attributes added to it. One is previous and the other is distance. So from A to A is a distance of 0. I don't need to travel, right? And I can say that the previous has the value undefined in it. Okay, so here I'll try and write it a bit smaller. So undefined. And before I've calculated anything, I would say that the distance to any of the other nodes is actually infinity. Okay, when you go to implement it in a programming language, you might just want to define infinity as a constant with a really, really large number. So let's say 100 million or something like that. That way you will never think that, it is a realistic distance or it is a short distance that should not be overwritten. Okay, so I'll keep going. Undefined, infinity, infinity, infinity. Now I will, what I will do is I will consider A first. So once you've said, okay, I'm going to consider this, I'm processing this, you can color it with red, okay? Now, its neighbors are C and B. So for each of these, I look at the distance from here to there. So it is 0 to get to A plus 6. Okay, is 6 better than infinity? Absolutely. So I'm going to go with 6. And instead of my previous being undefined, no, my previous node would be A. For C, same thing. 0 plus 3. So 0 plus 3 is much better than infinity. So I'm going to say 3, and my previous is A. Now what happens is I finished with this. Okay, so what I'm going to do is I'm going to start taking up either B or C, whichever one has the smaller value in the distance attribute. So in this case it is C, so I'm going to go with C. Again, I'm now processing C, so I can color it red. You can color it red at the end of processing, okay? It doesn't really matter as long as once considered, that's it, we don't go back to it. So what are its neighbors? E and D. So for E, the distance to get to E, remember, my entry point will always be A. This is not saying from any other entry point. So from A, the distance is 3. I've already calculated this. I don't have to recalculate it. Okay, plus 12, which is 15. Is 15 better than infinity? Absolutely. What is my previous node? C. So if I update this, I update this as well, because it means I'm finding a new route to this node. So again, I come to D and I say the distance is 3 plus 5. So the distance on the node I'm processing plus the weight of the edge to this one, which is 8. So I've updated this. I need to say, where do I come from to get a distance of 8? C, right? Now, no more neighbors that I haven't considered. So now what I do is of the unprocessed nodes, so B, D, and E, which one has the smallest distance? That's the next one I am going to process. Well, in this case, it'll be B. Okay, processing B. Okay, so to come to E, I need 6 plus 8, which is 14, better than 15. It's 14. The process of updating distances like this, by the way, sometimes is called relaxing the distances, okay? Again, I've updated this. I have to say, well, to get this better distance, I need to come through B. All right? So, again, from B, the only neighbor that hasn't yet been processed is E, so I'm done. Okay? Of the unprocessed nodes, which is the one with the smallest distance? It will be D. Let's consider D. So its neighbors that haven't yet been processed are E and G. So to get to E from here, I've got a distance of 8 plus 3, which is 11. Okay, you won't always be updating, but when you can update, that's a good thing because it means you are finding a quicker route. So to G, the distance will be 8 plus 20. 28 sounds like a lot, but actually it's much better than infinity, isn't it? Having updated this, I need to say I do that by coming from D. Okay, of the remaining unprocessed nodes, E is the one with the smallest distance. Let's process E. So its neighbors are F and G. Let's see, to get to F, I've got to travel, basically the cost of getting to F will be 11 plus 5, which is 16. To get here at a cost of 16, I'd better be coming from E. Now, to get to G, I have a cost of 11 plus 9, which is 20. Again, I only get this lower cost if I come through E. All right, what is left unprocessed? These two. This is the one with the smallest distance. So I'm going to be processing F. And in here, so from F, G is the only neighbor. The cost would be 16 plus 2, which is 18. Again, we need to update this. Then the only thing remaining is G. I take it out. I say, yep, this is being processed. It's got no neighbors that are yet to be processed. So I've now figured out the shortest path from A to each one of these other nodes in my graph, or in my network, if you prefer to call it that. And this is how Dijkstra's algorithm does it. Now, in this example, we have done things visually in such a way that it's probably easy for us to practice, okay, on paper. In a programming language, the idea of seeing which, each time having to look at every single one of the unprocessed nodes, especially if we have a lot of nodes, and seeing which one has the smallest distance is not very efficient. And then having to check, among its neighbors, which ones have been colored red or not is also not very efficient. So we will worry about efficiency in upcoming examples. For the time being, I hope you can follow the Dijkstra algorithm, and I hope that you will practice with a few networks of your own. Thank you. Oh, no, not yet, not yet. So let's say I want to find the shortest path to node F. Well, I can always backtrack now because I know I have to come through E. So let me just get the highlighter and highlight with a different color. So I can come through E. And E tells me the most efficient way to get to me is through D, which in turn says the most efficient way to get to me is through C, which in turn says please come through A. I come here and the previous is undefined. That's how I know I'm at my starting point. So the path really is So the shortest path to F from A is A to C to D, finally to F. The way you would write a path would be a set of edges. So it'll be the edges AC, CD, DE, and finally EF. So this is the shortest path. I do hope that was clear enough. If not, maybe it's worthwhile going through the video a couple of times, practicing on your own network, and there are lots of other video explanations that might be better than mine, so you can feel free to check them out. Thank you.